So now on to some more complicated rules for taking derivatives. So the first one is going to be the product rule. So suppose f of x and g of x are differentiable functions. So this is going to be kind of like my linearity rule from the last section. So I'm not going to be given f of x and g of x. I'm going to be given a function, but as I look at it, I'm going to see that that function is actually composed of two simpler functions multiplied together. And if I can take the derivative of each of those simpler functions, then the product rule is going to allow me to take the derivative of the product of those two functions. So suppose I'm given a function p of x, and I can see a way to write it down as a function of f of x times a function g of x, and I want to take the derivative of p of x. So p of x is differentiable, and the derivative of p of x, so p prime of x. So my definition of p of x is just the product of f of x and g of x. And the product rule says that the derivative of this is going to be the derivative of the first function, so f prime of x, times g of x, plus the first function, so f of x, times the derivative of the second function, g prime of x. And so I think the best way to deal with this is just to go through some examples. So in several of my slides, I start out the slide with recall. That's just to remind you what the product rule is. So this is just the definition of the product rule here. And suppose my function p of x is x times e to the x. So right away, I'm going to recognize this. This is the product of a function f of x equals x and another function g of x equals e to the x. And I know how to take the derivative of both of those functions. So I'm going to kind of skip in this course all of the rules for taking derivatives of functions. These are easy things to look up now. I actually brought my phone here because I found out that Siri, which is the voice assistant on an iPhone, one of the things that it asks for sources of data is Wolfram Alpha, which is this website I've been recommending to you. So I'm going to try an on-screen demonstration of this, see what happens. What's the derivative of the exponential function?
Checking on that. Here's what I found.
Okay. So I don't know if the camera is going to be able to pick that up, but it shows up this little, I don't know what that's supposed to be. Actually, that's a dot matrix printer paper. But it actually has the derivative of the exponential function on it. Although they used a capital X and I used a small x. But otherwise, it's exactly what I wanted. So the point is, and I'm going to remember to switch off the ringer now, otherwise I will get embarrassed. You can use a lot of tools. Google would probably find the correct answer for this. If you have a computer algebra program like Mathematica or Maple, you're going to be able to ask it questions like that. You can look this up in any number of calculus textbooks. So kind of going through all of these rules, I'm going to skip that. But when you come to a function that you don't know how to take the derivative of, there are lots of tools available online or in the library that will help you figure out how to do that. So what we just found out from Wolfram Alpha via Siri was that the derivative of this function, e to the x, is just itself. So it's a special function that has the property that it's its own derivative. So this one will be the easy one to take the derivative of. And this isn't going to be too hard either. You can think of x as just x to the 1 and use the power rule. So you get 1 times x to the 1 minus 1, or 1. So I'm going to break this up as f of x equals x, g of x equals e to the x, and then just evaluate this. So what I end up is derivative of x is 1 times e to the x, plus derivative of e to the x, which is itself, times x. And then I'm just going to do a little bit of grouping like this because I think it looks nicer. But either this or this line, these would both be acceptable answers for the derivative. So for my second example, I defined p of t. So here, there's no real difference between using x and t. That's just the variable. I can call it anything I want to. A lot of times t shows up as kind of a variable name for time. X shows up for position. S shows up for an asset price. It doesn't matter. You do everything exactly the same regardless of how you choose to label the parts of your function. And so p of t is defined to be the square root of t times the quantity 1 minus t. And so I'm going to look at this, and I'm going to say, well, if I want that to be a product, the simplest thing is going to be the square root of t as f of x and 1 minus t as g of x. And then to make taking the square root possible, I can rewrite that as t to the 1/2 power. And so this is just another way to express roots. So if I wanted the cube root of t, that would be t to the 1/3 power, and so on. And it's a lot easier, I think, to take the derivative when it's written like this. It's just very clear that you can use the power rule. So now that I've defined my f of t and g of t, I'm just going to take their derivatives and then plug the pieces into the product rule. So the derivative of t to the 1/2, that's by the power rule, just going to be 1/2 times t to the 1/2 minus 1. So 1/2 times t to the negative 1/2. Then times g of t, so times the quantity 1 minus t, plus t to the 1/2, so that's my f of t. And then the derivative of 1 minus t, we have to sort of, in our head, use the linearity principle and the power rule at the same time. So this says that I can take the derivative of g of t is going to be the derivative of 1, which is a constant, so it's 0, and the derivative of minus t, which is just going to be negative 1. So that's where this minus 1 comes from. It's a derivative of minus t. And then I can do a little bit of simplification. Replace the t to the 1/2 with a square root of t, if you want to, and maybe mess around with it a little bit to make it a bit more pretty. But again, once you're this far, you've successfully taken the derivative. And the rest of this is just to make it a little bit more presentable. So the next rule I want to talk about is called the chain rule. This is probably the most important rule and where you will make the most mistakes. So again, we're going to talk about two differentiable functions, f of x and g of x. And so last time we thought about multiplying them together. This time we're going to think about evaluating, how did I do this? So f of x, taking the result of that and feeding it into g of x. And so that's called a composite function. The textbook uses this notation. All it means is, so g composed with f of x is, g evaluated at f of x. I find it a lot more sensible just to always write it down like this. Anytime I've tried to write it down like this, I end up confusing myself. So I prefer this notation. So if f of x and g of x are differentiable functions, then the composite function g of f of x is also differentiable. And the derivative of this composite function is the derivative of the outside function, so derivative of g of x evaluated at f of x times f prime of x. And so like I said, I really don't like this notation of the composite function. I tend to confuse myself. So another way you can write this is using something called Leibniz notation, who is just another mathematician. And so what you do is you think of it in sort of two steps. So first, I'm going to evaluate f of x, and that's going to give me a number u. And then I'm going to evaluate g at that number u to get my final answer, g of f of x. And the chain rule then says that the derivative of g, so the derivative of the outside function, with respect to x, which is the argument of the inside function, is the derivative of just g with respect to its argument times the derivative of u, so the argument for the outside function, with respect to x. And I think this will be clear once I start doing some examples. So like I said, this is called Leibniz notation. So first I'll try and do a few using, using this funny composite function notation. So if I say g of f of x is equal to the square root of x squared plus 1, then I sort of have to look at that and say that this has to somehow be two functions. So the two functions I see are x squared plus 1 and then the square root. And again, just to make this a little bit simpler, I'm going to write the square root as this quantity to the 1/2 power. And that's going to hopefully stop me from making quite so many, I suppose, typographical errors while I'm writing this out. And so the chain rule then says that the derivative of g composed with f is going to be the derivative of g. So that's just going to be 1/2 times the quantity x squared plus 1 to the 1/2 minus 1, so negative 1/2, then times f prime of x. So here the f of x is x squared plus 1. And so by the power rule, I can see that x squared, its derivative is just going to be 2x. Then 1 is a constant, so its derivative is 0. So I end up multiplying this thing by x. And then I can rewrite my 1/2 power as a square root again. This 2 over here is going to cancel out my 1/2. And so I get a little bit nicer looking format once I simplify a bit. And you can do the same thing. This is one of the examples from the textbook. It's exactly the same problem as this one up here, just with some different numbers. So I have something on the inside, and then the outside function is that raised to the 100th power. So when I take the derivative of that, first I'm just going to say 100 times the quantity to the 100 minus 1, so 99. And then the chain rule says, to get the derivative right, I also need to multiply this by the derivative of the inside. So that gives me 3x squared over here. And if I simplify, this ends up being the derivative. If instead we think about this using the Leibniz notation, the way I want to set up problems is using something called substitution. So suppose I want to compute the derivative of the sine of x squared. Well, if I just look at that as one function, I don't know how to take the derivative of that. But you can see right away that you do know how to take the derivative of sine. If you don't, you can ask Siri or Google, search Wolfram Alpha. So what I'm going to do is define a new variable u that's equal to x squared. And now if I replace x squared with u, I would know how to take the derivative of this function. And so that means my function g of u is just going to be sine of u. So it's sine of x squared. If I replace x squared with u, I just get sine of u. And then I'm also going to need this du dx over here. So I'm going to get that just by taking the derivative of this. So the derivative of u is just going to be 2x. So du dx is going to equal 2x. So if I take the derivative, and this is where you have to be a bit careful of not getting variable names confused. I'm taking the derivative with respect to x of the sine of u. And so that what the chain rule is telling me is, if I want to do this, I can just take the derivative of sine of u with respect to u. So that's this first term in the chain rule. And then I need to multiply that times the derivative of my substitution. So here I've substituted u equals x squared. So I have to take the derivative of that and multiply it in to whatever I get here. And so now I can just go ahead and start evaluating derivatives. So you can look up the derivative for the sine function. You'll find that it's cosine of u. And the derivative of u with respect to x, that's easy to get from here just by using the power rule, is 2x. But now I still have a u in my answer here. But I can just undo my substitution now by going back and saying, well, u is equal to x squared. So I end up getting the correct answer here, 2x times cosine of x squared. And so another example, suppose I try to take the exponential of sine of theta, and I want to take the derivative of this with respect to theta. So here I see two functions. The inside function is going to be the sine function, and the outside function is going to be the exponential function. So what I'm going to do is I'm going to let u be the value of the inside function. So I'm going to make the substitution u equals sine of theta. And then I'll fill in the rest of the pieces like I did in the first example. So g of u is then just going to be e to the u. So I get that just by looking at my original function and making the substitution u equals sine of theta, or sine of theta equals u. And then I also need the derivative of my transformation, or of my substitution. So du d theta is just going to be cosine of theta. So if I take the derivative, derivative of this here, with respect to theta, I'm just going to get cosine of theta. And then I just start plugging things into the chain rule. So I get the derivative with respect to x. That should be a theta there. So derivative of e to the sine theta with respect to theta is the derivative of e to the u with respect to u times the derivative of u with respect to theta. Derivative of e to the u, well, we've already seen this. This was this special function that's its own derivative. So that just stays. Where did my mouse go? Oh, that's not good. Okay, there it goes. That just stays e to the u. Du d theta becomes cosine theta. And now I have this u here, which I don't want anymore because the answer should be in terms of theta. So I just have to substitute backwards. And I get the final answer, cosine of theta times e to the sine of theta. And then just one last rule. So if you have an inverse function, so an inverse function of a function f of x is a function f inverse that just gives me back the argument. So it sort of undoes whatever my function just did. So if I take f inverse of f of x, I just get x back. And you have to be a little bit careful here because f has to be sort of a function where this is going to work. So if I did something that was periodic, like if I looked at a sine function or a cosine function, that's very easy to take the x variable and get a y variable. But if I just tell you the y variable, there's going to be a whole bunch of x variables that will give you that same y variable. So you have to define it on a region where it's one-to-one both directions, so that I can actually do this and get exactly the same x back that I put in. And so f inverse is then just going to be a function. So f takes a point in AB and gives me back a point in CD. And f inverse is just going to take that point in CD and give me back my original point in AB. And I have to choose these intervals so that that is unique, so that I can go forward and go back and get the same answer for all of the points in the interval AB. So then there's a rule for computing the derivative of the inverse function. And so as long as this thing in the denominator is not equal to 0, then the derivative of the inverse function is just 1 divided by f prime evaluated at the inverse function. And so just as a quick example, consider log of e to the x. So these are functions that are kind of undo one another. So log of e to the x is always equal to x. So I'm going to say my function f is e to the x. F prime of x, so e to the x is this special function that's its own derivative. So f prime is just e to the x. And then f inverse is going to be the log function. And so if I look at the derivative of log of x, it tells me that I should just take 1 divided by f prime, so that's e to the x, evaluated at f inverse. So f inverse is log x, so it's e to the log x. And so just like we had log of e to the x was x, here I have e to the log of x is also x. And so that tells me that the derivative of the logarithm is 1 over x. And again, you could ask Wolfram alpha, what's the derivative of the logarithmic function? And it's going to tell you it's 1 over x. Okay, so just a quick summary. We had the product rule. So that said the product of two functions, f of x and g of x, was just, sorry, the derivative of a product is the derivative of the first function times the second function plus the first function times the derivative of the second function. We had the chain rule. So I like this notation a bit better. So it says that the derivative of a function is the derivative of the outside function times the derivative of the inside function.